Hi, welcome to the third lecture on complex analysis. This is going to be the first lecture on differentiation of functions from C to C. In the last two sessions, we were dealing with or focusing on functions from an interval in R to C. Today, we are going to talk about functions from an open subset of C to C and talk about its differentiation. Okay, and so today we will look at something and we will also derive the algebra of such functions and introduce some jargon like holomorphic functions, analytic functions, or whatever they are. Okay, we will do that, and we will also give some non-trivial examples. Okay, let's get started. Yeah, so this is complex analysis, holomorphic functions 1. Yeah, this is for characterization of differentiability, and it's used to establish the algebra of differential functions. Okay, watch my videos. I'm just showing so that you'll know how to look for it. Okay, yeah. So let us go to the thing. So what are we going to deal with? We are going to deal with U, an open set, and non-empty, of course, as usual. We will assume that. So what does it mean? Given any Z in U, there is R positive such that the open disk BZR is completely contained in U. That is the definition of this. May be my U. Give me a U, then there exists one R, and give me this exists like that. Okay, there is an R such that the open disk is contained on that. Right. So what are we looking at? We are going to talk about differentiability of function. So fix a Z or make it A in U. Fix. I want to say F is differentiability A. How do I define? Exactly as we did from R to R, or even from R to C in the last two sessions. How do I define? Remember, since A is a thing, there is an R such that BAR is completely contained in U. Therefore, every Z in BAR, FZ makes sense because Z lies in the domain of the function. Therefore, what do I want is look at f of Z minus f of A by Z minus A. So this limit as Z goes to A should exist. This is our definition. If the limit exists, then we denote it by f dash A and call it the derivative of f at A. Okay, so this is standard definition. And just to recall the limit, I had already done from metric space to metric space in my first session on functions from R to C. So I don't have to spend time again and again. Okay, you ought to learn these things. There is no point in repeating the same thing here. Okay, so this is the definition. So it's a no difference. Okay, exactly from real analysis or also for functions from R to C, it's exactly the same definition. So let's just recall, this means give me any epsilon positive, there is a delta positive, so that if the distance between Z and A is less than delta, then the distance between Fz minus Fa by Z minus A minus F dash A is less than epsilon. Okay, if there exists F dash A a complex number with this property, if you want to call it lambda, there exists a lambda so that this happens. That lambda is denoted by F dash A. Okay, very good. This is the definition. There is nothing more to do. Alright. So you have the standard examples as usual. Okay, constant functions will always be differentiable, etc. But before that, let me say, if f is differentiable at every z in U, then we say f is holomorphic. In classical thing books, okay, it's called analytic. Okay. In modern analysis, the word analytic function has a separate different notation, different meaning. That's why I avoid that word. In fact, all modern mathematicians will try to say holomorphic rather than analytic. Okay, so it simply means holomorphic. Yeah. Holomorphic. Holomorphic. Okay, it simply means differentiable on an open set. So remember, when I say a function f is holomorphic, two things are needed. What is that? The domain of f must be an open set, and second thing, the function should be differentiable at each and every point of the domain. Then only we say it's holomorphic. Is that clear? Make sure that you understand this. Okay, right? Before we go to some examples, as I said, okay, the two examples are obvious. Let me just finish it, but we will generate more. One is constant function. If f of z, let us say, equal to alpha for every z in u. Okay, then f is differential. Why? Because I can take fz minus fa by z minus a. This will be 0 by z minus a, which goes to 0 as z goes to a. Therefore, any constant function is differentiable. Differentiable. And the derivative of dash z is 0 for all z in u. And second thing is the easier one again. Okay, let us do f of z equal to z. I can also do z power n, but let me just do z in open set u. Then it's again easy. F of z minus f of a by z minus a will be z minus a by z minus a, which is equal to 1. It goes to 1 as z is a. Therefore, the identity function f is differentiable and its derivative is f dash z is 1 for all z in u. Okay, right. I can do for z squared also, z power n, but I will do that. Before that, I want to talk about a characterization. Those of you who had gone through, I just see I'm sharing it, yeah. Those of you who have gone through my lectures on differentiation of functions from R to R in real analysis will know that I am very fond of a characterization of differentiability. So let us look at that characterization. Notice that these two functions, what I did, this is what happened last time also. Something happens, I don't know why. Yeah, I hope you can see this. Oh, it's the same problem, yeah. Right. What is the characterization? Let f from u to c be given. Then f is differentiable at a in u if and only if there exists a function f1 from u to c such that f of z is f of a plus f1 of z into z minus a and 1 for all z in u, and 2 f1 is continuous at a. Okay, and if you have gone through my lectures on real analysis, this is very easy. The proof is identically the same proof, but if you are a newcomer to this channel, I'll just give this proof, but when I'm going to use to, okay, let's see. Okay, so the proof is easy. Suppose f is differentiable at a. Let lambda equal to f dash at a, right, because it's differentiable at a, therefore, right. Now let us look at, I want to find an f1. Remember, for every z in a, this first equation should hold, right. When z is not equal to a, then f of z minus f of a by z minus a must be equal to f1 of z. If first equation holds, I am just working backwards. If the first equation should be true, then my f1 of z is clear. It should be f of z minus f of a by z minus a, right. But remember, f is supposed to be defined on all of u, therefore in particular at a it should be defined. But then remember, it says f1 must be continuous at a. Yeah. So this is my f. If this is my f1, therefore what should be my f1 of a then? Since f1 is going to be continuous at a, then that should be a limit of z going to a of f of z minus f of a by z minus a. Therefore it must be f dash of a. Okay. Please understand, if again you are new to my channel, I am working backwards. Okay. A typical proof will be like this now. Okay. So let us assume f is differentiable at a. I have to find f1. So simply the teacher will write, define f1 of z to be f of z minus f of a by z minus a. Z is in u, z is not equal to a, and equal to f dash of a. That's it. Then f1 is as desired. Okay, this is verification now, right? Whereas we arrived at f1. Okay, pause, review, proceed. Now converse part. Suppose f1 is given satisfying 1 and 2. Okay, then I want to show f is differentiable at a. Right, this is what we want to show. Right. Okay, so to show that, what is that I have to do? I have to look at f of z minus f of a by z minus a, where z is in u, right. But notice that this is by definition, since f of z, f satisfies 1, therefore f of z is f of a plus f1 of z into z minus a, therefore this is nothing other than f1 of z or z not equal to a, right. Therefore what do I want? I want limit z goes to a of f of z minus f of a by z minus a. Okay, since this object is equal to limit z tends to a of f1 z, and since f1 is continuous at a, this is nothing other than f1 at a. Okay, so now we can even say the theorem a little more. So this looks like that. It's the same mistake. So if I don't know how to stop that. So what have we shown? Now let's go back. So it shows that a characterization, if this happens, so we are adding. If this happens, that means such an f1 exists, then f dash a is nothing other than f1 of a. Yeah, right. So pause, review, proceed. Let me use it to prove the third example now. That's the reason why I didn't want to do that. The third example is, let us look at u to be c, my f of z equal to z power n, where n is a natural number. Right? I want and fix an a in c. I want to know whether f is differentiable at a. So what is that I would look at? I would look at f of z minus f of a. Again, if I gone through my analysis course, I will not produce what is f1. What I will do is, how do I get my f1? F of z minus f of a must, I should write it as, this is the trick, you should remember how to find f1. Okay, write f of z minus f of a, do algebraic manipulation, write something times z minus a. If you succeeded in that, this star is your f1 of z. Are you following? That's what I am going to do. So I will not take this as f1 and verify that. So this is going to be z power n minus a power n. But remember, what is that I want to do? I want to write it star times z minus a, but all of you know how to do that. All of you know this. This is z power n minus 1 plus 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 a to the power n minus 1. So what is my f1 of z? Z to the power n minus 1 plus z to the power n minus 2a plus a to the power n minus 1. And is this continuous at z? Because this is a polynomial in z, therefore it's continuous. Okay, is continuous on c. So, and what is f1 of a? At z equal to a, I have to do, but if I put z equal to a, this is a to the power n minus 2 into a, that is a to the power n minus 1 and so on. Therefore it is n into a to the power n minus 1. Therefore, what is the derivative? N into a to the power n minus 1. Therefore, the derivative for n is z is n into z to the power n minus 1. Do you love this proof? Yeah? Are you tempted to go back to my real analysis course, learn differentiation in a much better way? Okay, right. Okay, pause, review, proceed. And let's look at one more example. Suppose I want to prove f of z equal to 1 by z. My u is now c star. Right? Then how will I do that? The same thing. So look at f of z minus f of a, which is 1 by z minus 1 by a. And therefore what is common? Z times a. Therefore it is a minus z. Right? But this is minus z minus a by za. Right? Now therefore what should be your f1? f1 of z should be minus of z minus a, because this is equal to z minus a into star. But what is that star? That is my f1, that is z times a. That's z. Okay. And what is f1 of a? Minus 1 by a squared. Therefore what is f dash of a? By the way, is this continuous? Okay, f1 is continuous, that's clear. Right? I want it to be continuous at a, but it is continuous at all points also on c star anyway. So it's continuous. Right? So f dash of a is this. Therefore f dash of a is 1 minus a squared. Therefore f dash of z is minus 1 by z squared. So pause, review, proceed. Okay, from this it follows the so-called algebra of differentiable functions. So what does it say? The standard thing, let us say U is an open set. Okay, A is a point which is differentiable at, okay, let Fg, okay, be differentiable at A. Then what are the things I want to say? For every lambda in complex number, lambda f is differentiable at A, and 2 f plus g is differentiable at A. What is f plus g at A? Z. This is by definition f of z plus g of z. Okay, and third, f times g is differentiable, and what is the derivative? F plus g dash at z is f dash z plus g dash z, and f times g is a differentiable at A, and what is f g dash? That is f dash into g plus f into g dash. Okay, and what is the fourth one? Fourth one is, suppose f, okay, is not 0 at A, but before this, okay, right, I will come to that little later. Just look at these things. Okay, all these things are very easy. For example, how will I do 3? I'll just show that. So I'm not going to give thing. This is going to be f of A plus f1 of z into z minus A, right? There exists a function f1 which is continuous at A with this property. Similarly, g of z. Therefore, f of z into g of z is f of A into g of A plus f of A into g1 of z plus g of A into f1 of z. Yeah, right? This is whole times z minus A, and the next one is f1 of z g1 of z into z minus A whole squared. Yeah, but remember, what is that we want to write? We want to write it as f of A into g of A plus some phi 1 of z, call this phi as f times g, phi 1 of z into z minus A. Right? So there is a z minus A here, there is z minus A whole squared, therefore I can take it as f of A times g of A plus f1 of A into g1 of z plus g of A into f1 of z plus f1 of z g1 of z into z minus A, and the whole thing multiplied by z minus A. Right? Therefore this is my phi 1. This is continuous at A? Yes, because remember, this is constant, g1 is continuous at A, therefore this product is continuous at A, and this is GA is a constant, sorry, this is f of A, and GA is a constant, and f1 is continuous at A, therefore this is continuous at A, and f1 times g1 both are continuous at A, therefore the product is continuous at A multiplied by first degree polynomial z minus A, that is continuous at A. Therefore the entire thing, namely the defining expression for phi 1, is continuous at A, right? Therefore I have shown phi of z equal to phi of A, this is phi of A, plus phi 1 of z into z minus A, where phi 1 is continuous, right? Therefore what is the derivative? Derivative is phi 1 of A. But what is that? That is f of A into g1 at A, that is nothing other than f of A into g dash at A plus g of A into f1 at A, that is f dash of A, plus, remember when I put at A, I don't care what this is, actually this is f dash at A, g dash at A, but 0, therefore this is just 0. Therefore this is the answer, right? Therefore what is phi dash at z? Phi dash is nothing other than f g dash plus f dash g. Yeah, do you have understood? So pause, review, proceed. So in similar way, in fact the other things are much simpler, you can prove it. But before going any further, I want to show this. If f is differentiable at a, then I want to say f is continuous at a. Okay, that is very clear. Let us look at what is f of z. F of z, since f is differentiable at a, there is an auxiliary function f1. I will call it auxiliary function. Okay, so that this is f of a plus f1 of z into z minus a, right? Therefore, this is for every z in u, right? Now let's look at f of z equal to this. This is a constant function, therefore it's continuous. And z minus a is first degree polynomial, therefore it's continuous on all of u, right? This is a constant function on all of u, therefore that's also continuous. Now f1z is this is a function on u, but it is supposed to be continuous at a, therefore this is continuous at a. Therefore the entire right side is continuous at a. That means f is continuous at a. Do you like that proof? See, if you have not seen this characterization, learn that well, because unfortunately I have been trying to use this for last 30 odd years, but teachers and textbook did not catch up on this. Okay, this is a very beautiful way of looking at differentiation. Okay, pause, review, proceed. Okay, now let's look at, now suppose f from u to c is differentiable at a and f at a is not equal to 0, right? Now since f is, this is my u and this is my a, this is not differentiable at some point, that means there is an r so that f of z is not equal to 0 for all z in bar, which is by continuity. Right? If f of a is not 0 and say if f is continuous at a, there exists. I hope all of you know that, how to prove all such things. Okay, this is just a metric space thing. Okay, you must all learn in real analysis and again in metric spaces, etc. Right? Therefore, if I define g of z equal to 1 by f of z for z in bar, which is contained in u, okay, g is a function on bar to c, right? Now I want to know whether g is differentiable at a. Is the question clear? Right. Now how will you do that? It's the same thing. So how will I do that? So g of z minus g of a, but g of z is 1 by f of z. G of a is 1 by f of a, where these are all z in bar. So what do you think I will do? I will take fz into fa common, therefore it is fa minus fz. Yeah, but remember, since f is differentiable, okay, there is an auxiliary function, and so that f of z equal to f of a plus f1 of z into z minus a. Therefore this fellow is nothing other than minus f1 of z by f of z into f of a, right? Okay, into z minus a. I'm sorry, I should also write z minus a. Yeah, right. Therefore what will be my g1? If I define g1 of z to be minus of f1 of z by f of z into f of a, okay, is this continuous at a? This is true for every z in bar. Notice that this is true for every, this one, this inequality, this is true for every z in u, in particular for every z in bar also this is true. That is, namely fa minus f of z is minus f1 z into z minus a, right? Okay, this is continuous at a. Why? because this is a constant. F of z, f of a is not equal to 0, therefore 1 by f is continuous at a, and f1 of z is continuous at a, therefore this is continuous at a, and therefore what is g1 of a? That should be the derivative of g. This is nothing other than minus f1 of a by f of a whole squared. But what is that? That is minus f dash at a by f of a whole square, right? So this shows g dash is nothing my f dash by f squared. This is the standard formula you must have seen. Yeah, right. Next thing is chain rule. I will come to that later. See, all these things follow very easily by using my characterization. So it's good to learn that thing very well. Okay, good. Now let's take a break. Let's go to examples now. Therefore, any polynomial function is differentiable on C, right? Suppose f of z equal to a0 plus a1z plus n z power n, right? We proved the power functions are differentiable and scalar multiplication of these things are differentiable and sum of differential functions is differentiable, therefore this is differentiable. And what is its derivative? That's as you can expect. Again, f plus g derivative is f dash plus g dash, therefore this is going to be derivative of a0 constant, and this is a1 plus etc 2a 2z plus n z power n minus 1. Okay. Next, suppose I take a rational function. Okay, that is a polynomial. Let me write polynomial p of z by another polynomial q of z. P and q are polynomials. Notice that we have seen p of z, this is differentiable on all of C, and q of z is also differentiable, but q of z, 1 by q of z is differentiable whenever q of z is not equal to 0, right? Therefore, if I look at z of q to be complex numbers z and c such that q of z is 0, remember q is continuous, therefore this is q inverse of 0, and this is a closed set, therefore this is a closed set. Therefore, if I take c minus 0, this is an open set, right? Therefore, p by q, call it f, this is a function defined on c minus z of q to c, and by the algebra of differential functions, okay, this is differentiable. F is differentiable on c minus set of roots of the polynomial q. Okay, pause, review, proceed. Yeah, okay. Now let's look at next example. We already know any power series function is differentiable on its disk of convergence. So let us look at a power series z minus a to the power n 0 to infinity, and let us assume r is a radius of positive radius of convergence, it may even be infinity. Then we know if I define f of z, the sum cn z minus a to the power n 0 to infinity, this is differentiable on where? On BAR. This we have seen in my third lecture on power series. Third lecture exclusively dealt with complex power series, where I proved any complex power series is term-wise differentiable, right? Therefore this is differentiable. Okay, And what is the derivative? We also know the derivative is nothing other than n Cn z minus a to the power n minus 1, where n is from 1 to infinity. Okay. So notice that whatever you have done so far is all functions are holomorphic on the domain of definition. For example, z power n, this is holomorphic on C, and power z is C and z minus a to the power n is holomorphic on, it's a disk of convergence, and the rational function p of z by q of z, this is called a rational function. This is holomorphic on C minus the, look at the zero set of q, that is set of point z such that q of z equal to 0. Okay, remove that. This is an open set, on that it's holomorphic, right? Okay, now let's go look at, before I enter the lecture, let us look at one more example. We already know, if I look at exponential of z, this is z power n by n factorial 0 to infinity. Here the radius of convergence is infinity, therefore it is convergent for every z in C, right? And we also know it's differentiable. Right? Okay. Now this is a definition. If a function f is holomorphic on C, the entire complex plane. I am using the word entire complex plane so that I can say that. Then f is called an entire function. Therefore, exponential is an entire function. Right? And polynomial is an entire function. Rational functions need not be. Why? If q is a non-constant polynomial, okay, there is at least one alpha, a complex number, such that q of alpha is 0. Right? Therefore, the domain of definition of p by q, okay, in the domain of p by q will not contain alpha. Right? Therefore, a rational function need not be entire. Do you accept it? Okay. Now let's go to one or two trivial examples. Now I can define for every z in C cos of z to be exponential of iz minus plus exponential of minus iz by 2. Okay, and notice that exponential z going to exponential iz is differentiable, and similarly this is differentiable, and this is 2, not z. Okay, therefore this is differentiable, and this is therefore, and hence it's also entire. This will have a formula, if I remember right, minus n z to the power 2n by 2n factorial, n is running from 0 to infinity. And similarly sin z is defined, that is exponential of iz minus exponential of minus iz by 2i. That's it. Look at the imaginary part. That's all it means. Are you following what it means? Yeah, right. So this is going to be, I hope I'm right, minus 1 to the power n and z to the power 2n plus 1 by 2n plus 1 factorial, n running from 0 to infinity. Okay. Remember, these are all convergent power series. Therefore, algebra of convergent series, infinite series, you can apply to work out these things. Okay, these things you should do, or you can always look at my book. Okay, if you want, refer to my book or any book. There are simple algebra, except the analysis comes. I am going to add term wise. Okay, nth term of exponential iz and nth term of exponential minus iz. I add, then I will get sin z. Okay, so it will be an infinite series, right? I am using algebra of convergent series. It's not pure algebra. Okay, learn that. Similarly, you can define cos h of z, that is exponential of z, plus exponential of minus z by 2, and sin h of z or exponential of z minus exponential of minus z by 2, etc. Okay, so all these are all entire function. That is, these two trigonometric function cos, sin, hyperbolic function cos h, hyperbolic function sin h are all are entire function. So we had given lot of examples of differential function. So naturally we have to give an example of a non-differentiable function. Let us look at, okay, this is a non-example. Let us look at f of z equal to z bar. Okay, where z is in C. We claim f is not differentiable at any point, at 0, but at any point. Okay, let us look at that. So what is f of z minus f of 0 by z minus 0? That is going to be z bar by z. Okay, does it have a limit? There, does this tend to a limit? No. Why? Because if z take z equal to r or e power I theta, then z bar is r e power minus I theta. Therefore, z bar by z will be e power minus 2 I theta. Right? So this goes to this because it's a constant. Therefore, as r goes to 0, this goes to e power 2 I theta. Therefore, the limit is not unique. Right? Therefore, we know it is not differentiable at 0. Now, the same thing you applied to is not differentiable at any a. How will I write? Write z as a plus r e power I theta. Okay, do the similar trick. Okay, I leave this to you. So I hope you enjoyed this. So complex differential functions are no different. Okay, right. But in the next lecture, what we are going to do is I am going to give a non-trivial example of a differential function, which is never ever done in books or courses, but you will appreciate it as we go along because it's a result and the kind of ideas of the proof which I am going to do there, they will be recurring theme. Okay, you will appreciate that, and I am going to do the simplest case so that the ideas become crystal clear. Okay, and that will be the second session. So till then, take care, stay safe.